Hello, assalamu alaikum. Can you hear me?
Walaikum assalam, sir. How are you, sir?
Alhamdulillah, I'm fine, thank you. Okay, just we're waiting some minute, then we'll
Right.
start our today's session.
Oh, okay. No problem. No problem.
Okay, so we will start this session. So basically, today is our fourth number DELS. Okay, so let me share my screen. So after completing the 3 hours live training, then we talk about the problem solving. Okay, for the previous classes, anyone any problem, then we discuss about that after completing the 3 hours live training session. Okay, can you see my screen? Is it visible? Can you see my screen?
Yeah, it's okay.
Okay, thank you. So let's continue. So basically today I discuss about that how to remove and cloud and haze from your satellite imagery, mainly Landsat Sentinel, how to remove cloud and get the neat and clean satellite imagery. We also discuss about that and also discuss about the DEM data, digital elevation model, this DEM data, how we can easily use and create the different types of topographical mapping, such as hillshade map, then slope map, or aspect map. So this type of DEM data, how we can easily use and create the different types of topographical mapping. We also discuss about that. And another thing we also discuss about that LST, basically land surface temperature monitoring. Land surface temperature monitoring also discuss about that. Using Landsat or MODIS satellite imagery, how we can use and create the LST. We also discuss about that. And how to calculate average, maximum, minimum NDVI for any specific region. We'll also discuss. And after LST, we'll also discuss about that urban heat island, how we can easily connect the urban heat island and identify the urban heat island, and also discuss about that urban thermal field variance index to compute the effect of urban heat island, and how to make the time series chart of LST. Also discuss about that. So let's go discuss about that one by one, all of topic, then you can easily get the idea. And for today's session, you can also get one kind of research topic. It's very popular. We can easily use the LST, urban heat island, and urban thermal field variance index, and we can easily publish this type of different types of paper regarding this type of topic. Okay, so okay, let me show you some paper, then you can get the more better idea. So let me open, suppose. Suppose if you check, this is the one kind of paper. So assessing and predicting the land use, land cover, land surface temperature, and urban thermal field variance index using Landsat imagery, Dhaka metropolitan area. Then this is another same concept also used this in this paper. It's a modeling the impact of land use, land cover changing pattern on urban thermal characteristic in the Kuwait. So basically, this two paper concept is similar. Okay, not much any difference. So if you just follow this type of paper, not only for you can get a lot of paper already work this type of topic, LST or land surface temperature or urban heat island, okay, as well as urban thermal field variance index. Okay, then we can easily get. If you check this paper, so let me show you the algorithm or method. Then we try to implement this method in our code. Hmm. So if you check, this is the one kind of paper. So in this paper, basically they are use here Landsat satellite data for 2 season. Okay, summer season as well as also use the winter season. Okay, so they are use the 2 season of land use, land cover, then urbanite island or LST. Okay, simply use the 2 season. You can see this is the first season. They take the data for summer season, okay, for this time, and also get the winter season. Okay, basically summer and winter, then make the comparison. Okay, and also make the land use, land cover classification and classified the water body, urban area, vegetation, barren land. Okay, and further they also apply the artificial neural network for predicting the land use, land cover for future. Okay, so if you check, there is the Landsat data. We also discuss this type of things when I talk about the, I think it's a 6 number class for land use, land cover classification. Then I also discuss this type of things. So today's session I discussed about that LST. Okay, how we can easily compute the LST and also compute the urban heat island and also compute the urban thermal field variance index. So this is the LST, how we can easily use the Landsat data and make the LST, as well as we also discuss about that urban thermal field variance index, how we can easily identify estimating the urban thermal field variance index, as well as urban heat island, how we can easily identify. So this type of thing we try to discuss, then you can get the better idea. Okay, so not only for that, if you check some other paper about that, suppose let me simply search LST monitoring using Landsat. Simply search, then you can get the different types of paper. They are already work for LST computing. Okay, let me just open from the research get. Simply search here or just from the Google. Let me show you that LST. LST. Yeah. Okay, so let me open it. Just open a flowchart or algorithm. Okay, so you can see this is the another algorithm for another paper. So they are also used at the Landsat satellite data, Landsat 8 satellite data to compute the LST, land surface temperature. So if you check this data set, that take the mainly 3 band, thermal infrared band, then near infrared band, also red band. So these 2 bands simply use and compute the NDVI. After that, compute the vegetation proportion, or also compute the surface emissivity. Okay, and after that, compute the land surface temperature using the mono window algorithm. They are also applying here. So this is the one kind of paper. Not only for that, lot of paper is already published regarding this type of topic. You can easily check this type of paper to get the idea what types of algorithm they're using in here. So let's we try to follow, and then we just simply develop a code to compute LST, urban heat island, and also urban thermal field variance index. So first of all, we need to simply import our study area. So let me open the code editor. So first step, simply import your study area. Okay, suppose in this case, I import my specific boundary. So here I already uploaded my shapefile, which I work. Suppose I work for the Dhaka city boundary. Just I imported my study area, and further it show the default variable name is the table, but you can use any name. Suppose I put the name is it's my ROI. Okay, so this is my study area. Suppose I want to focus and also add the layer of my boundary. So simply use the map.add layer and display your boundary, and also focus on your given study area. Yeah, then focus in your given study area. So this is my study area. So this area I want to monitor land surface temperature. Okay. So now these things you can monitor for the different season or different year. Okay. You already know about that. I already discussed for the previous class how to get the collection for the summer season and also rainy season. Okay, so I hope you also know about that, how to create the seasonal image collection. So when you work with the seasonal image collection, simply filter the image collection seasonally, summer season, rainy season, or winter season. Okay, simply filter your image collection. So for now we need the image collection. So simply just click the browse data catalog, and then click on the Landsat. I want to work with Landsat image collection. So here you find out Landsat collection 2. I want to so Landsat 9. Or Landsat 8, 7, or others keep the same. Just only change the band name. Other word is the similar. And if you check the surface reflectance, so this reflectance you always use to compute the land surface temperature. So now simply copy the snippet ID from here. So this is the image collection of Landsat 9. Just take copy and give a variable name, suppose image. So now this image collection I need to filter. So now you can easily filter the image collection for seasonal, summer season, rainy season, and also compute the LST for the different season. So now I want to create, suppose, first of all, filter bounds to intersecting with my study area, so RY. Then put at the filter metadata. So I choose this, then suppose one. Then filter red. Suppose I want to compute for summer season or rainy season. So any specific season or a specific year. Suppose I just need the data. Suppose I create for 1 year. So I put suppose 2024 1st January from, or create for suppose 2025 1st January from 2025. If you check the time period is that 29 December last time period. Okay, so December 29. Okay, so 1 year almost we take the data. So now if you check how many images, we find out that, so just I call the image and put here the size function to compute how many images we find out in this collection. So let's compute only for the 8 images, we find out that less than 1%. Okay, between this time period, we find out that only for one image is available. Yeah, less than 1% cloud cover, we find out that. So if you simply increase the level, suppose cloud level, suppose I put the 10%, so now this image is also increased the number of total image collection 14%. But we always try to keep the less than lowest cloud cover image. So we try to always, when you work, so this is the main target. But some place or some season, mainly for rainy season, or any place near to the river bank or coastal area, so this type of place is very difficult to identify less than 1% image. So then we need to increase this value, and when you increase the cloud level, we find out some cloudy pixel on our satellite images. So today's session I also discuss about that how we can easily remove this type of cloud and get the very neat and clean satellite imagery. So after some time we'll also discuss about that. So in this case I just keep only for the one less than 1% cloud cover. I find out the total 8 images. So now these 8 images, I create the composite. I apply median composite and further clip with my study area, which is RY. So now I want to display the image. So just map.add layer of this image and run the code. So now you can easily get this imagery. We find out this type of imagery look like that. Now if you want, you can also add the color. Suppose I put here the red, then green, and blue. Okay, and if you check, it's a digital number. Okay, dn value. So this dn value need to convert to reflectance value, but in this case it has a problem. If you check, mainly when you work with land surface temperature, we need to use the band. It's called the surface temperature or brightness temperature. Basically this is called the stb10. Okay, stb10. So this is the band. It's also called the thermal band. It's mainly stored the temperature or band 10 surface temperature. And basically this band, okay, it's called the thermal band or band 10. Okay, band 10. So if you check this band, scale value is different. You can see this is the another scale value and another offset value. But if you check, this type of bands are this type of values. This type of values. Okay? Basically B1 to B7, all of bands are the keep the similar scale and similar offset. Only we find out that different for STB10 and also STB10. You can see this is the another scale and another offset value. So now when I use this scale value, just I copy and then paste. Okay, just a minute. So now if you check, we simply we need to use the scale value for the specific band, but we find out that is the similar band. Okay, so now we need to just select some band. So for that, they already give a solution. If you check, they already create a function. Okay, so in this function, basically they are add all of bands SRB1 to SRB7, all of band ST SRB, you can see all of bands. Okay, as well as also add the STB10. Okay, and multiply this band, basically two different scale value and two different offset value. Okay, so now we can easily use the function, okay, and apply. So otherwise it creates some problem. So when I just use only for the one scale, then suppose this scale is a different scale, but when I just apply only for this scale, so then it also use the same scale for this band, but this band have the another scale value. So further we simply copy this scaling factor code from here. Basically they create a function, so just I copy and I paste above this collection, and this thing basically they write create a function. So if you want you can also use it this way, just I copy the variable name, and before the variable name use the var keyword and paste the variable name and equal sign. So now we can also use this type of way to write the function. Okay, so it create a function. So in this function basically optical bands basically SRB1 to SRB7, and thermal band STB10. So these optical bands and thermal band simply multiply their own scale value and offset value. Okay, and create a and connecting optical bands and also thermal bands. So now this function I simply apply in my collection. So before the median, it's called the collection. So I simply apply here dot map and call this function variable name. So now it simply connect. Okay, so now if I run the code, we can get the proper scale value for all of bands, STB10 as well as also optical band as well as a thermal band. So we find out that if you just simply add, suppose just click on here. So now we can get the proper scale value. Now I am to add the color. Suppose SRB4 red, then green and blue. And further stressing I keep 98%. And then apply. So now you find out this type of imagery. So this image I want to use to monitor LST, land surface temperature. I want to monitor. So this is the process. I simply import the visualization parameter in my code editor. So this is the process for scaling optical bands, mainly SRB1 to SRB7, and also thermal bands, basically STB10. So these two different bands have the two different scale value. So that's why we simply create a function and doing these things. Okay. So now I just copy the visualization parameter from here and paste after the object name, and then put the layer name. I put any name. I put the name, suppose image. Run the code. So now we find out our image. Okay, so this is the image we find out. So now I want to use the image and compute LST, land surface temperature. So if you check the different types of research article, so almost all of article are the similar method, not much any difference. So this is the final equation of the LST. Okay, so in the LST if you check, we need the K1 and K2 calibration contains one in this unit we find out. So you can see this type of thing. Okay, this one you can also can see the brightness temperature estimation. Okay, they use this and calculate the brightness temperature. And if you check, this is the NDVI, their compute same equation, near minus red divided near plus red, and you can see the final LST equation. Okay, so in the final LST equation if you check, LST equal to land surface temperature, TI, it's basically represent the sensor brightness temperature, and also you can see the immediate radiance wavelength indicating as a lambda, and we also get the long emissivity indicate the spectral emissivity of the land surface. So in this equation if you check, we need to compute this TI basically brightness thermal band or sensors brightness temperature or brightness temperature STB10. Then we also need to compute the emissivity. Okay, so this type of things how we can easily compute. So let's go one by one to discuss. So first of all, also you can see the another algorithm. Let me show you that this one. So you can see, first of all, I simply compute the NDVI. Then we compute the vegetation proportion. Then we simply use the surface emissivity, okay, from the vegetation proportion. After that, the both of band we simply use and apply the mono window algorithm and compute the LST. So this is the one kind of paper. So first step, we simply compute the NDVI. Okay, we already know about that, how we can easily compute the NDVI. So, okay, let me write the code for NDVI. You already know because we already discussed about that, how to compute different types of calculating the different types of indices. The first step, when you make the LST, first step, compute NDVI. Okay, so for the NDVI, what is the formula? We already know about the formula. This formula is the near infrared band minus red band divided by near infrared band plus red band. So when you compute this equation, then we can easily get the NDVI. So it's very easy, you already know about that. And this equation we can compute different way. Okay, so previous class I already discussed about the different way to compute the different types of equation. Okay, so for that, now I simply create a NDVI. So take a variable NDVI and then call the image. I simply apply the normalized difference function to compute NDVI. So this formula we already know about that, SRB5 near infrared and SRB4 red, and they are the two element. So for that we need to make a list, square bracket start and square bracket int. We simply put in here. So now when I just simply add the layer of NDVI, so map dot add layer and call the NDVI and run the code. So we can easily get the NDVI map for our study area. So this is the first step. Simply compute the NDVI. So if you want, you can also add the color, or if you also ignore this part, there is no problem. Okay, let me add the color to visualize the NDVI map. So for just I stress 98%, and then I simply add the color. Suppose this type of color. Okay, then also use here this type of color. Then also use this type of green color for vegetation. Then apply. So now it's added this type of map. Just I import the visualization. So this type of green color indicating about the vegetation area. Okay, vegetation area, this type of green color. Just copy the visualization parameter from here and paste after the object name of NDVI, and then give a layer name. I put the layer name, suppose NDVI. So this is the first step for NDVI computing. Then second step, we need to compute a vegetation proportion. Okay, vegetation proportion, basically these things we need to compute PV. Okay, and if you check, the vegetation proportion formula is NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value and then power 2. So this is the proportion of vegetation. It also called fraction of vegetation. So these things we simply compute, but for that I need the two value, NDVI minimum value and NDVI maximum value. I need when you work with the PV, proportion of vegetation, when you work. So I need the NDVI minimum value and also need the NDVI maximum value. Then I simply apply this equation and compute the vegetation proportion of vegetation. Okay, so let's go try to compute. So it's called the PV or FV. Okay, fraction of vegetation or proportion of vegetation. So this thing when you compute, we simply compute the NDVI minimum value and also NDVI maximum value for my study area. Okay, so for that, just take a variable suppose I put the variable name, suppose max equal, call the NDVI because I want to compute the vegetation maximum value, and apply the reduce region. So this function basically it's compute the statistical value when you compute. So in this case I want to compute the average, sorry, maximum value. Okay, so for that we need to apply this function for a specific boundary. Okay, not only for that average. When you compute, suppose maximum, minimum, average, or standard deviation, or any statistical value for a specific boundary, not multiple boundary, only for the specific boundary. For the multiple boundary we also use another function, but this function is only work for a specific boundary. Suppose in this case only for Dhaka city boundary, this it's a specific boundary. So then we can easily apply the reduce region function to compute the different types of statistical value for this NDVI. Same like as for LST. Suppose I make the LST map. So now I want to compute the maximum LST value or minimum LST value or average LST value. So this type of things we can always use the same function, reduced region function. So from the NDVI, I want to compute maximum and minimum value. So just I use the reduced region and then fill up all of argument. So first argument, it's called the reducer. Reducer, I want to compute suppose maximum. So EE dot reducer dot max, and then apply another one geometry. Basically it's your shapefile variable name ry. Then scale. Basically it's a resolution. So scale is 30 meter. So now we simply use these things, just take a variable max and call the NDVI and apply the reduced region function, and I want to compute the maximum value, okay, for my study area, a specific boundary, a specific region of interest, and also 30 it's our scale value. Okay, so these things we simply use in here and compute the maximum value of NDVI for our study area. So for that, simply print this result, then you can easily get the value. Just print this max. So now it display the result, maximum NDVI value for my study area, and it shows as a dictionary. Okay, you can see it's a dictionary. And what is the dictionary means? Dictionary have the keyword and key value. So when I click, we find out the keyword and key value. So it's called the ND and it's called the value. Okay, so we find out the maximum value of NDVI is 0.8. So the 0.8 is the maximum value of NDVI. But now this result display as the dictionary. You can see dictionary. So now this dictionary, I just need to convert only for the value. Only for the value without dictionary. So for that, simply use here the dot values function to extract the value. Only extract the value. Use the values function and run the code. Now check what happened. So now it work as a list. Okay, you can see now it work as a list. In the list, we find out the 0. It's the first item and it stored the value. Okay, so now put here the dot get function and apply the 0. So now from the 0, I get only for this value. So when I run it, if you check, so now it computed object and display only for the value. So first time it was a dictionary, mainly keyword and key value. So from the dictionary, I just extract the value. So for that, simply use the values function. And from the values, I can get the first item. So just apply the 0. Then I can get only for this type of value. And this value work as a computed object. Okay, it work as a computed object. But now I want to use it as a number. So for that, simply use a function ee dot number. Okay, and also the bracket. So now when I run, you can see what happened. It show the result as a number computing. So now this variable stored the number, and this number I can easily use for any other equation. Very easily I can use. The same concept we also use to compute the minimum value of NDVI. Just I copy the same line of code and then change the variable, suppose min, and I put the function min minimum, and I want to print this variable min. So now I can easily compute the minimum value of NDVI for my study area. So this two value you need when you work with proportion of vegetation, okay, PV or FV, proportion of vegetation, because you can see this equation is NDVI minus minimum value of NDVI divided by maximum value of NDVI minus minimum value of NDVI then power 2. So this equation, when you compute, you need the two value, minimum value and maximum value. So this two value I simply computed in here, minimum and maximum. So now I can easily apply the equation. So just take a variable. Suppose I put the variable name is PV, and then apply. Just I call the NDVI. I already compute NDVI in my case. So from the NDVI, I want to subtract. So apply the subtract function. Subtract from minimum value. Or let me check the equation again. So again, this is the S and V. Okay, so PV is the represent the proportion of vegetation. NDVI minimum value. NDVI mean value. Yeah, sorry. This is the NDVI mean. S mainly small. So this small value is simply used. So minimum value. So just I call the mean. Okay, and then divided by maximum value, subtract with minimum value. Okay, and this full equation power 2. Okay, just I bracket the full, covered the full equation and put the POW power 2, and 2 is a number. So when you define any number in server, we always use the function ee dot number and then define the power 2. So now we can compute it. So now we can compute it the PV or proportion of vegetation. Okay. So this proportion of vegetation, I simply, if you want, you can also add map.add layer and call the PV and run the code. So now it also added the proportion of vegetation layer. Okay. Further, if you want, you can also add the color, but it's optional, not need mandatory now. So now we simply get the PV. So after computing the proportion of vegetation, we need to compute the emissivity. Okay, so emissivity value we need to compute. So for that, okay, so it called the em emissivity. So em equal PV, proportion of vegetation, multiply 0.004 plus 0.986. So this is the equation of the emissivity. So when you compute this equation, we can get the result of em or emissivity layer. So for that, we already compute the PV. Okay, so now just take a variable, suppose em, and call the PV. I already compute the PV. Okay, so this PV simply multiply. So put here the multiply function, and it's a number. Okay, so when you define any number, we need to use the function ee dot number. Okay, and then put the value 0.004, then put the add function, and it's a number ee dot number we define, and call 0.986. So now it's computed em or emissivity layer. We simply find out in here. Okay, so now if you want, you can also add the layer, map.add layer of em and run the code. So now it also added the em layer, emissivity layer. We have to find out in here. So it looked like that. So let's add the proper color. Further, if you want, you can also add the color. Just apply now. And also import. So this type of blue color indicating about the low emittance value, and this type of red color indicating about the high. So just I import these things, and further just copy the visualization parameter and paste after the object name, and put the layer name EM and run the code. So now you find out this type of layer or EM. Okay, so this is the way we compute the emissivity, and now we simply compute the it's called the brightness temperature. Basically, if you check the paper, it's called the brightness temperature, the TI, brightness temperature. So this thing we simply computed. So it's called the brightness temperature, or STB10. This layer we can easily identify from here. So for that, compute brightness temperature. So take a variable. So I put the variable name is that thermal, or you can put any name, thermal. When I simply put the thermal, and from the image I call my image. So I already have the image. So from this image I just choose only the thermal band. So thermal band, what is the name? So this name is STB10. STB10. Just a copy and paste here. Okay, and this STB is already completed the rescaling. Okay, you can see already rescaling. So that's why I not need now, because I already rescaling these things. So now if you want, you can also display the thermal band. So simply just apply map.add layer and call the thermal, this variable. Just run the code. Okay, so it look like that. If you want, you can also stressing to get the more better visualization. Again, this thermal band, it's a brightness temperature, and this temperature unit is Kelvin. Okay? Further, we also convert into degree Celsius. No problem. So just import. If you want, you can also add the different types of color, but it's optional. So it's called the brightness temperature. And it's a thermal. So now we find out this type of things. So now we apply the final equation of LST. So if you check, the final equation of LST is Ti temperature, brightness temperature divided by 1 plus lambda multiply Ti divided by rho multiply logarithm ln emissivity. So in this case, if you check this type of value, rho value, it's a constant value 1.4838 multiply 10 square inverse 10 inverse 2. This value it's indicating, and also you can see the ace is basically indicating the Planck's constant. So this is the equation about that. Okay, rho equal to these things, and also you can see also constant value. So now this equation is simply simplify. Okay, simplify. So basically in this case we just simply use the Ti and also emissivity, but others this lambda and also this rho, this type of values is the constant value. So this type of constant value is simply simplify and then only use the Ti value and also use the emittance value, then we can easily compute the LST. So let's go. So for the LST, just take a variable, suppose LST is equal, just I call the thermal, and then use your expression, and this equation when you simplify, then we can simply write, suppose Ti, okay, Ti divided by 1 plus 0.00115. Let's simplify these values and then multiply Ti, okay, brightness temperature Ti divided by 1.438, and these things, this equation we need to multiply logarithm of EP, mainly emissivity or EM, we can put anything, no problem. So this Ti and EP, EM, emissivity. Okay, so now this is the equation. Okay, this is the full equation. So in this full equation, when you subtract the value from 273.15, then you can get the result degree Celsius. So just simply minus 273.15. So now this Kelvin unit convert into degree Celsius. Okay, so now put the comma sign and put the dictionary, curly bracket start and in, and now define what is the Ti and what is EM. Okay, that is the constant value. So now simply define what is the Ti. Ti, it's basically come from the image, basically this, and select for specific, basically this thermal band. Okay, so we already selected, or you can also directly use the stb10 in here, because now stb10, this band is stored in this variable, so I simply choose it. Okay, then comma, then what is the EM. So just write here EM. So this EM, it's come from emissivity, basically from here. Just I copy the EM and use in here. Okay, so now finally just I add the layer. So I have to add layer of LST and run the code. So now it's added the LST layer. We find out in here, but we face a problem. Okay, so let's check the problem. Okay, so band selector. Okay, we make the mistake in here. This mistake is we already, this thing is stored in this variable. Okay, so now I just use only for the thermal. So now let's check. It look like this white color. So let me check the result. And if you check, it show the stb10. Okay, it show the stb10 because we are not use the rename. Okay, So if you don't use the rename, then it show the fast band name. Okay, fast band in this equation, fast band is the STB10 or thermal band. Okay, thermal band. So that's why it show the default STB10 band name. Okay, so not only for that, if you check others, suppose this layer, it show what is that. If you check this thermal layer, so it show the STB10 because it's just only for the one band. Okay, no problem. So let me check the second one. If you check this one, it's a EM. When I use the PV, so this layer it show the PV. So let me open the EM layer. If you check, it show the ND. Okay, it's default. It's a default name ND. So now this type of things how I can solve. So for that, if you want, you can also use here the rename function. So I put the rename function dot rename, and I put the name. Suppose it's a LST. So when I rename as a LST, so then it also change in here. So now run the code and check what happened. So now it show the result as a LST. So if you check, it show the LST. Okay. So now further apply the stressing and display the just let me just add the color. Suppose low temperature greater than use this type of color greater than use this type of color greater than use this type of color, or any color combination is simply use. So now apply. So I find out this type of LST map. Okay, or you can also check the different types of stressing level, which one is more beautiful. You can also keep it. Just like this thing, can check, we find out this type of, suppose if I put the stressing level to sigma, now apply this. So now suppose I just use it, so just import. So now this code is added in our code editor, and copy the variable name and paste after the object name. Okay. And then put the its LST layer name. So now these are final output. We find out this type of LST. So this LST can easily compare with the winter or summer. Okay. So this paper behind work, it just mainly work for that summer and also winter. So both of season, it just compared. And also for urban heat island, both of season, and also urban thermal field variance index, both of season. So now we find out this type of LST. So we find out this type of place have the high temperature, this type of red color. If you want, you can also check the temperature from the inspector tab. Just click. So now it show you that for this coordinate, how much temperature, 35.33 degrees Celsius. And this type of blue color, it show the low temperature due to the water body or vegetation. Okay, it show the low temperature due to the vegetation area. Okay, and this type of place mainly for construction or concrete or barren land. So this type of place explains the very high temperature. And water body or vegetation, this type of place we find out the low temperature. So this is the overall LST mapping using Landsat satellite imagery. This concept you can also use for the any Landsat image collection for the different time period, as well as you can also consider it for seasonal LST or also winter LST or summer season LST. So different types of LST. So now anyone in question, you can ask me about the LST. Any question about LST, you can ask me. I hope there is no question. So let's go and continue again. So now we talk about that urban heat island, how we can easily monitor. urban heat island and compute and detect the urban heat zone. Okay. Okay. Let's continue. And further, you can also export it as a GeoTIFF file format. Okay. And how to export, you already know about that. We also discuss about that, how to export this type of GeoTIFF file. Again, further work with the ArcMap, import easily. So now we talk about that urban heat island. So our USI or urban heat island, it refers to the phenomena in which urban areas experience significantly higher temperature than their surrounding rural areas or rural region. Okay, this temperature difference is most pronounced is at night and during the calm or clear weather condition. So lot of region, okay, for that urban heat island, suppose concrete or rooftop absorb the store the solar radiation during the day, okay, and remit it as a heat at a night. And loss of vegetation, okay, a loss of vegetation basically reduce the evapotranspiration due to the fair trees and green space limit the natural cooling. Then urban geometry, mainly canopy effect, okay, dense building trap the heat and restrict the airflow. Okay, so it restrict the airflow. So this is the another main cause for urban heat island, as well as also anthropogenic heat. Okay, so basically in the Dhaka city or any other city, for the heat released from the different types of vehicles, air condition, industries, or human activity. So this type of anthropogenic heat also release. Okay, and we find out that mainly for the city area, lot of vehicles they are released a lot of heat. Okay, we mainly face this type of things. Okay, as well as in the city area we find out the very loss of vegetation. Okay, and when lost the vegetation, it reduce the evapotranspiration. Okay, suppose some place there is no tree, some place there is no tree, it means that this place reduce the evapotranspiration due to the fair trees or green space limit natural cooling. Okay, as well as we also find out that lot of concrete or construction, lot of concrete. So this type of concrete or construction, it absorbs the heat. Okay, so this type of region we find out that urbanite island in the city area. Okay, so we find out the high temperature, okay, than the rural area. So now this urbanite island, how we can easily compute, we discuss about that. So for that we need the LST or land surface temperature. So when you compute the urbanite island, you must need the LST. So you already compute the LST. So now, so if you check some paper, so if you check this the one kind of equation, also check the citation about that. So this is the seasonal variation within a year. LST is compared in that regard. Normalized method is adapted. The follows equation. This is the citation. So this is the formula. So this formula, if you check, it show the USI equal TS, mainly LST, LST minus average LST divided by the standard deviation of LST. So when I compute the equation, I need the two value, average value, and also need the standard deviation of value of LST. So then I can easily compute these things and then compute the Arvanite island. So let's go try to compute. So Arvanite island equal to, you can say it's a LST minus mean LST divided by STD DEV LST or standard deviation LST. So this is the equation. I already compute the LST. So now I simply compute the average LST and also compute the standard deviation of LST. So same process. We already know about that. We need to use the reduced region function. Okay, reduced region function. So if you want, you can also use the same line of code. There is no problem. Just a copy to compute the average LST. Just a paste and I put the variable name, suppose LST M. or average LST. And then just call the LST variable, because this variable is straight the LST map. Just take copy and paste. I want to compute average, so put here mean, and then just call this LSTM and print. So now it's computed in the Dhaka city average LST value, average land surface temperature value. It's computed. We find out the 31.72 degrees Celsius. So now, same way, we simply compute the standard deviation of LST. Just take copy the same line of code and paste here, and I put it's a LST STD. You can put any variable name, no problem. Then put here STD EV. Just copy and paste here. So now it's computed standard deviation of LST in Dhaka city region. So this is the way we simply computed the standard deviation of LST and also compute the average LST. So now I can easily apply this formula, okay, and get the urbanite island zone. So let's go and try to compute this equation. Take a variable USI and call the LST. This LST minus. So minus means subtract with average LST, LSTM, I already computed, and then divide with LST standard deviation. Just a copy and paste here. And now further we simply add the layer. Then put here urban Italian and run the code. So I can easily get the result for urban Italian zone. So now if you check, we find out this type of place, basically this type of white color indicating about the very, very high temperature. Okay, so basically it create the binary class. Suppose this type of place is urban heat island zone. This type of white color, it's the urban heat island zone. Okay, and this type of place is not much temperature. Okay, so if you want, you can also use the color and display. Suppose I just use the two color and display the urban heat island zone and non-urbanite island zone. Okay, so just again the 0 and 1, and I put the color. Suppose where there is no urbanite island zone or low temperature, I want to use one color. Suppose I want to use this type of color, and where is the high, I want to show this type of color. This two color I want to use. Just apply. And then import. Now paste here the hidden parameter and put it's a USI. Okay. So now we find out that this type of red color, it's the more temperature. It's very high temperature. So now you find out this type of hotspot, this type of red color indicating about the host hotspot of urban heat island. Okay. So now this type of place indicating about that urban heat island hotspot. This type of red color indicating about that. So this type of place, suppose due to the concrete or barren land or rooftop, so it absorb and store the solar radiation during the day and re-emit it as a heat at night. Okay? As well as this type of place have not mass vegetation. Okay, and if there is no vegetation, then we find out that low evapotranspiration due to the fair trees and green space limit natural cooling, as well as also canopy effect or urban geometry. Urban geometry, basically we find out the dense building and density building, or where we find out the dense building. This dense building, we find out the trap heat and it restrict the airflow. When you find out the high dense building, this type of high dense building, it restrict the airflow. As well as a lot of vehicles, they release the heat, as well as air condition or industries or human activities. So then we find out this type of place. So it's called the urbanite island to identify. So now we try to identify effect of urbanite island. Okay, if you check. Okay, so urban thermal field variance index. So this index mainly identify effect of urbanite island. Where is the high effect? Where is the low effect? It's identify. Okay, this is the another index estimating the urban thermal field variance index. And if you simply search, suppose let me search here, urban thermal field variance index trends. Values. Okay, so if you check, okay, let me check the one. Okay, so if you check this type of things, um, urban heat island phenomena are almost same. Okay, let me open anyone. So you can see this type of chart. So if the index value is negative, mainly less than 0, so it means that ecological evaluation index excellent. Okay. So basically negative value. So in this index, where I find out that negative value, it means that this type of place ecological evaluation index is very good or excellent. Then you can this trends it is a good, this trends it the normal, this trends strong, bad, worst, and very worst. We find out this type of things. So you can see this one kind of classification of urban thermal field variance and effect of urbanite island. Okay, if there is no suppose negative value indicating there is no effect of urbanite island, and you can see the positive value when increase, it's a strongest effect. Okay, high values indicating about the strongest effect of urban heat island. So now this how I can compute this urban thermal field variance index. So further we simply apply a equation, LST minus average LST divided by LST. So when you compute the equation, then we can easily get the result of urban thermal field variance index, and then we can easily compare this type of values, and we can easily identify ecological evaluation based on the UTFVI. Where is the excellent, where is the good, where is the normal, where is the bad. So this type of things we can easily identify based on urban thermal field variance index. So now we try to compute this equation, LST minus average